All right. So last class we looked at Pythagorean identities as well as refreshing our memory on some of the basic identities that we have looked at before to help us work with trig expressions. Today we're going to look at sum difference and double angle identities. So we'll apply sum difference and double angle identities to verify the equivalence of trig expressions, and we'll verify trig identities numerically, graphically using technology. So these identities are also on the formula sheet, so you don't have to memorize them. But on the next page, there's the sum identities for sine, cosine, and tangent. And again, they're on the formula sheet, so you don't have to memorize them. Okay, so those are the sum identities. And if you take calculus next year, you'll see, go through a proof of where these come from. So those are the three sum identities. The sine of a plus b is sine a cos b plus cos a sine b. And we have an identity for sum of cosine of two angles and tangent of two angles. So what you have to remember is that the sine of a plus b does not equal sine a plus sine b. It doesn't. Okay? And you can look at just a quick example of that in the calculator. So my calculator is in degree mode. So, and again, what I'm showing is that sine of a plus b does not equal sine a plus sine b. And just to quickly show that, if a is 30 degrees and b is, let's say, 70 degrees, well, then the sine of a plus b would be equal to the sine of 100, which we can do on our calculator. The sine of 100 is 0.9848. If you do it the other way, meaning sine of 30 plus the sine of 70, sine of 30 plus sine of 70, you don't get the same thing. You get 1.439997, excuse me. So again, this just shows that the sine of a plus b does not equal sine a plus sine b. But there is a relationship for the sine of a plus b, and we have it there in that blue box, as well as for cosine and tangent. Now, from this, you can get difference identities. Basically, as it says here, if you want to find the difference identity, sine a minus b, you take the sum identity and you replace b with negative b. Okay, and that's what it shows here. Replacing b with negative b. Shows it right there. So up here, wherever we see the b, we replace it with negative b. Now, when you have a negative rotation angle, we've talked about this before, that puts you in the fourth quadrant. So if we draw an xy axis here in our fourth quadrant, using our cast rule, that's our C quadrant. Cosine is positive. So that is why the cosine of negative b became the cosine of just b, because in the fourth quadrant, cosine is positive. So that's why the cosine of negative b became the cosine of b, and it's also why the sine of negative b became the negative sine of b, because again, you're in the C quadrant. Only cosine is positive. And so this negative goes in front, and that's where the difference identity for sine comes from. In the same way, we can get the difference identity for cosine and tangent by replacing b with negative b in the sum identities above. And that gives us our difference identities. And the third set are our double angle identities. So again, if you want to get the identity for sine 2a, which is a plus a, Once again, we can take the original expression for sine of a plus b, and now we replace the b with a, and that'll give you a plus a, which is 2a. So that b becomes a, this b becomes a, and that b becomes a, and that's where the double angle identity for sine comes from. It's sine a plus cos a sine a, sine a cos a plus cos a sine a. These two are the same expression, right? The two factors are just switched around, but when you're multiplying, order doesn't matter. So these two expressions essentially are the same. They both have a cosine of a times the sine of a, so therefore you add them together, you get two of them. So that's where the double angle identity for sine comes from. In the same way, you can get double angle identities for cosine and tangent, doing the same thing. Going up to the sum identities and replacing the b with the a and simplifying, you get these expressions. And again, they're on the formula sheet, so you don't have to memorize any of them. So we're going to see that there's a couple different uses of these. One of them being simplifying expressions, which are these first sets of examples. Another application of these sum difference double angle identities is allowing us to find the exact value of values that are not on the unit circle. For example, we're going to see that we can use these to find the exact value of the sine of 75 degrees as one example. 75 degrees is not on the unit circle, but using sum and difference identities, we're going to see that you can actually find the exact value for the sine of 75. But before we get there, again, one application of these is to simplify a trig function. And to do this, you just have to recognize the pattern. So this first example, or first question, you want to simplify this. It's sine 48 cos 17 minus cos 48 sine 17. We notice that there are some angles that are repeating. So if we say that 48 degrees is the same thing as A, and 17 degrees is the same thing as B, then this is sine A cos B minus cos A sine B. Sine A cos B minus cos A sine B. And if we look up here, that's that one right there. That mirrors, or that follows the pattern for the difference identities for sine. Sine A cos B minus cos A sine B. So this is the same thing as sine of A minus B, because that's what identity it represents. So again, this is the same thing as the sine of A minus B, or the sine of 48 minus 17, or the sine of 31 degrees. We've expressed it as a single trig function. We've simplified it. And just to show that these two give you an equivalent expression, if we take the original one, which was the sine of 48 times the cosine of 17 minus the cosine of 48 times the sine of 17. It's that decimal. Well, that should equal the sine of 31. And it does. So this just shows us that this relationship is valid. It's true. It works. For question B, you've got cos squared pi on 3, take away sine squared pi on 3. So again, we've got the same angle, pi on 3. If we originally say let it equal to theta, this would be cos squared theta minus sine squared theta. And if we look at our identities, that's this double angle identity for cosine. That's cosine 2a. That's the pattern. Cos squared a, take away sine squared a. So this is the same thing as cosine of 2a, or 2 theta. And in this case here, our angle for theta was pi on 3. So it'll be the cosine of 2 times pi on 3. So there, we've simplified it. We've expressed it as a single trig function. And once again, we can check this. We just have to make sure in this case that our calculator is in radian mode. It's the cosine of pi on 3 all squared. Take away the sine of pi on 3 all squared. Gives you that decimal, negative 0.5, negative a half. Well, if you take the cosine of 2 pi on 3, which is the answer we got simplified, you get exactly the same value. So again, that just shows that the relationship is true. It works. But what we've done is we've used them to simplify the expression, make it simpler. Right? And again, this is one of the applications of these sum difference double angle identities. But it starts with recognizing the pattern. So for question A, if we see that we've got 88 degrees, if we let that represent A and 35 represent B, the pattern here is cos A cos B plus sine A sine B. Well, if we look at our identities here, that's the cosine of A minus B. Cos A cos B plus sine A sine B. That is equivalent to cosine of A minus B. So for question A, it'll be the cosine of A minus B, or the cosine of 88 take away 35, which is the cosine of 53 degrees. So we've simplified it. We've written it as a single trig function by recognizing the pattern. So for question B, if we say that pi on 12 is letter A, this is 2 sine A cos A. They're both angles pi on 12, so they'll both be letter A then. And that is the double angle identity for sine. Right there. Sine of 2A equals 2 sine A cos A. Right, so for question B, for question B, 2 sine A cos A equals sine of 2A. And in this case here, our A value is pi on 12. So it'll be 2 times pi over 12 or pi over 6 when you reduce. So that original expression, 2 sine pi on 12 cos pi on 12, should be equivalent to the sine of pi on 6. So we'll check that. Making sure our calculator is now in radian mode, and it is. 2 times the sine of pi on 12 times the cosine of pi on 12 is that decimal, positive a half. Well, that should equal the sine of pi on 6. That's the simplified expression we got, and it does. So again, just proves that that identity is valid. It works. So you can always check these on your calculator, always, to make sure the expression you get at the end is equivalent to what you started with. So we saw earlier that cosine of 2A is equal to cos squared A minus sine squared A. But we're now going to see that there are two other variations for cosine of 2A. So this question wants us to determine the identity for cos 2a that contains only the cosine ratio. So to do this, we're going to use our Pythagorean identity that we looked at yesterday. And that is that sine squared a plus cos squared a equals 1. That's our Pythagorean identity. We saw that one yesterday. And we're going to use it a lot in this section. Now, we want to write cos 2a so that it's only in terms of cosine. So what I can do is take this Pythagorean identity and I can get sine squared a by itself by subtracting cos squared a from both sides. Once we know that the identity is true, then we can move things around. And so what I'm now going to do is I'm going to take this value of sine squared a, which is 1 minus cos squared a, and I'm going to substitute it above. So cos 2a will equal cos squared a, and we're going to subtract all of 1 minus cos squared a, which is why I'm putting it in brackets. You're subtracting all of it. I'm replacing the sine squared a up here with 1 minus cos squared a. When you remove the brackets, all the signs inside change. The 1 will become negative, the cos squared a will become positive, and now you have 1 cos squared a plus another one, which is 2 cos squared a's minus 1. This is a second variation of the cos 2a identity. Right? This is our first one. Now we have a second one. And we can do the same thing, only this next one asks us to write it so that it only contains the sine ratio. If we start with the original identity, in the last example above, we wrote everything in terms of cosine. Now this one wants us to write everything in terms of sine. So again, it'll start with that Pythagorean identity. And I'm going to get sine squared a by itself by subtracting cos squared a from both sides. Sorry, I did that backwards. I want to get cos squared a by itself. By subtracting sine squared a from both sides. And now this expression that represents cos squared a will go up there. We'll replace the cos squared a with 1 minus sine squared a. And then we have another minus sine squared a that was part of the original double angle identity for cosine. And negative 1 sine squared a minus another one will be minus 2 sine squared a's. Okay, I'm just opening up the formula sheet so you can see that these other two are on there as well. All three double angle identities for cosine are on there. Try that again. Okay, so there. You've got all three identities for cosine 2a. There's only one for sine 2a, only one for tan 2a, but there are three different variations of cos 2a. And I've just shown you where they come from. They come from that Pythagorean identity. So we said that one of the uses of these identities is to help simplify expressions. which is what this next one is doing. We've got that expression. We want to talk about the non-permissive values and then simplify down to one of the three primary trig functions, and then we can use our graphing calculator to check to make sure. But we start with our non-permissive values, and our non-permissive values always come from the denominator. Sine 2x cannot equal 0. That's our denominator. And sine 2x, remember, is 2 sine x cos x. That's right from the formula sheet. That's the double angle identity for sine. And so neither sine x nor cos x can equal 0. And as we've seen, we saw this last class, that would mean that x cannot equal, now it doesn't tell us what to use, whether it's radians or degrees, so let's use degrees. X cannot equal 90 n degrees. Every multiple of 90 degrees is where either sine or cosine equals 0. So there's the restrictions. And you could confirm that by putting that original equation in the graphing calculator, the original expression. So the numerator in brackets, 1 minus cosine of 2x divided by, we don't need brackets for this because it's only one term, sine 2x. So if I'm going to graph this in degree mode, I'll change that to degrees. And my windows will need to reflect that. So if I go from negative 360 to positive 360 degrees with a scale of 90, and for my y values, I'm not sure what they should be, so I'll leave them between negative 10 and positive 10. That's what the graph looks like. If we go into trace and we let x equal 0, notice there is no y value indicated there. It's a non-permissive value. At 90 degrees, again, no y value indicated. That's actually where there's a vertical asymptote. Same thing at negative 90. Negative 180, that's not an asymptote there. It's in fact a point of discontinuity, because it looks like the graph goes through that. It's hard to see, but there's a break in the graph there. Sometimes if we choose zoom decimal, I'm not sure if this will work or not. Yeah, it won't, because it changes the mode. I was trying to get a little bit closer look at what's happening at 90 degrees and negative, or 0 and 180, I should say, to see if we can see the point of discontinuity, but can't. All right, so we've done part A. Part B, we want to simplify this expression. So when we talk about cos 2x, there are three different possibilities that we can use, and all three will work. It doesn't matter which one. Some will be easier than others, but they will all work, okay? So what I'm going to do here is I've got this 1, and I've got minus cos 2x. So just to show you, it doesn't matter which variation of cos 2x we use, I'm going to start with the first one, which is that cos 2x equaled cos squared x minus sine squared x. And I put it in brackets because it's all being subtracted from 1. On the bottom, there's only one possibility for sine 2x, and that is 2 sine x cos x. So the minus sign in front of the bracket changes all the signs inside. So I remove the brackets on top, changes all those signs. And as of right now, we can't cancel anything because we've got a trinomial on top. You have to be able to cancel the same thing in all three terms, and you can't. Okay, so we've got some more work to do. Can anyone tell me what 1 minus cos squared x equals? This part right there. From what? From the Pythagorean identity, that's right. We know that sine squared x plus cos squared x equals 1. We've already done this a couple times today. If you get sine squared x by itself, that would be done by subtracting cos squared x from both sides. So sine squared x equals 1 minus cos squared x. Well, 1 minus cos squared x is the same thing as sine squared x. I have another sine squared x term on top. And we can combine those two sine squared x's together. One sine squared x plus another one will give us 2 sine squared x's. And now, because we have a single term on top and a single term on the bottom, now we can start to do some canceling. We can divide top and bottom by 2. We can divide top and bottom by 1 factor of sine x. And that leaves us with sine x on top over cos x on the bottom, which is tan x. So we've simplified it down into a single trig function, one of the 3 primary trigonometric functions. That's what it's simplified down into, tangent of x. So that means the graphs should be the same. The one that we started with, which I already have in my calculator, I just need to change my windows back to what I had them at before. So when I graph it, there's that one back again. But we need to see that it is the same as the graph of tangent of x. So if I put that in as my second equation, it should draw it directly over the first one. It happens fast. And there it is. Same graph. So that means that our simplified expression is equivalent to what we started with. We verified it using technology. So we're going to do the same thing with this one. Sine 2x over cos 2x plus 1. What are the non-permissive values for this? Well, our denominator is cos 2x plus 1. That cannot equal 0. Well, we can subtract the 1 from both sides, and we'll get cos 2x cannot equal negative 1. But this one's a little bit different because we've got cos 2x. Like in the last one, it was sine x and cos x. Whoops, there we go. The denominator was 2 sine x cos x, so there wasn't a 2x there. So we've got to do this one a little bit different. And here's what we do. What if it was just cosine of x not being able to equal negative 1? Remember that cosine is the x value, and the only place it equals negative 1 would be at pi radians. That's the point negative 1 comma 0. So x cannot equal pi radians. And every multiple of the period after that, which is 2 pi m. So those are the restrictions if it was cos x can't equal negative 1, but it's not, it's cos 2x. So now let's say for cos 2x can't equal -1. And again, we have to look back and see what that number 2 does to the graph. It horizontally stretches it. Horizontally stretches it by a factor of a half. So our restrictions will be half of what they were above for just cos x can't equal -1. So once again, for cos 2x, that's the graph of cos x that's been horizontally stretched by a factor of a half. So everything will be half of what it was before. The x-intercepts would be half of what they were before, as well as the non-permissive values. So we would say then x cannot equal pi over 2 plus 2 pi n over 2, or pi over 2 plus pi n. There's the restrictions. And again, you could verify though that by putting that equation, that expression into the calculator and going every multiple of, well, not every multiple of pi on 2, but starting at pi on 2 and then pi radians away, which could either be negative pi on 2 or 3 pi on 2, you could verify that they are non-permissive values. The calculator will not give you a y value for those x values. Okay, part B. Now we want to simplify this. So again, we're starting with sine 2x on top over cos 2x plus 1 on the bottom. And for sine 2x, we have only one option. But for cos 2x, we have three different options. In the last example above, we use that cos 2x is cos squared x minus sine squared x. We can do the same one here if we wanted to, or we can use one of the different ones. And I'm going to use 2 cos squared x minus 1. And the reason I'm using that is because the minus 1 there will cancel with the plus 1 that was originally part of that expression. It just makes things a little bit easier. So when those ones cancel, you're just left with 2 cos squared x on the bottom. And now we can divide top and bottom by 2. We can divide top and bottom by a factor of cosine. And we are left with sine x over cos x, which once again is tan x. And we can verify that on our calculator to make sure. So it's sine 2x divided by, in brackets, cos 2x plus 1. And that should be the same graph as tan x. So again, when I hit graph, it's going to happen really fast. It'll graph the first one and then the second one directly over top. So that shows that the expression we got for a simplified value is equivalent to what we started with. And while we have the graph here, let's also check our non-permissive values. Now we set our non-permissive values in terms of radians. We started at pi on 2 and then every multiple of pi. Because my calculator is in degree mode, I'm going to switch those to degrees, meaning 90 degrees would be a non-permissive value, and it is. But the next one will be 180 degrees away. 270 is a non-permissive value. Negative 90 is a non-permissive value. But if we check 0, 0 works. 180. $180 will work. You get a value of y. Right? So we check to make sure that the graph of the simplified expression is equal to what we started with. As well, we check our non-permissive values. Okay, I'm going to stop there for today. I can't emphasize enough, though, that you need to do this practice because we're going to get into more complicated expressions to work with. And unless you have some base skills, you're going to have trouble when we get to the ones that are more complicated. So You need to do the practice on page 306. I will post those solutions to Google Classroom so you can check your work, but you really should do it.